So those of you who don't know me yet, I'm Mr. J. I'm the last physics teacher you'll probably meet for the entire team. After this, you've met all the physics teachers in J1. Alright, so we're going to do circular motion today, which is a little bit like kinematics. So it's going to be a bit slow at the start as we go through all the terms. This is a whole list of stuff that you should know. Yellow, yay, to match our fire t-shirt. Right? So it looks like a lot of things to know, right? But we'll break it out into three parts, which is introducing to you the terms for circular motion. Okay. This idea called centripetal force and centripetal acceleration. And lastly, we'll go through some interesting examples of circular motion. Alright? So before we start on circular motion, we should always consider what we already know. Where can we find circular motion? This is a bad picture, so never mind. I'll show you an easier picture. This is our Milky Way galaxy. Right? We are somewhere inside it. You all know where? Yeah, it says here. So we're about 2/3 away from the center. Alright, that's us, our solar system, all the planets, all the friends and relatives that you have and whatever know are here. Right? So our solar system orbits the center of the Milky Way galaxy in a circle that looks somewhat like this, somewhat circular, it's actually elliptical, but a circle is a good enough approximation. So the sun moves around, and how long does the sun take to complete one revolution? Well, it's pretty long, 2.5 times 10 to the power of 8 years. Right, that's many years. Right, 250 million years. Right, so we'll let me go around one. How big is this radius? Well, it's 2.5 times 10 to the power of 17 kilometers. Come back to Earth, things are a lot more humane. The period in which our moon, our natural satellite, orbits the Earth is about 27.3 days, or approximately slightly less than a month. So you see the phases of the moon, the full moon goes to a crescent moon, it takes roughly a month. Right? And the moon transcribes a circle of about 400,000 kilometers. So the moon moves in a circle around the Earth. Any other things move in a circle around the Earth? Haha, not the sun. The Earth moves around the sun. Anything else moves around the Earth? Right? This is our natural satellite. Of course, we got artificial satellites. One of our most notable of which is the International Space Station, which takes about an hour and a half to go around the Earth once. Right? And it has a radius of orbit 6800 kilometers, the bulk of which is actually the entire radius of the Earth. So actually its altitude is only 400 kilometers. So it's only 400 kilometers above the surface of the Earth. The bulk of it is actually the radius of the Earth. So when we describe the radius of circular motion, what we are describing is the circle whose radius points towards the center of the circle. So of course for the Earth, any object reasonably near the Earth, a big bulk of the radius is taken up by the Earth's actual radius. Right, is there anything else going around in circles around the Earth? Other than our natural satellites and artificial satellites? How about us? Are we going around the Earth in circles? Yes, right? So even us at the equator, we're traveling around the circle, we're traveling a circle around the Earth simply because the Earth is rotating and we are moving around the Earth. Right? But some people will be traveling in smaller circles than others. For example, if you're in London, London is somewhere in the northern hemisphere, the circle in which they move when the Earth rotates is actually a lot smaller than the circle in which we rotate. Right? Because ours is the equatorial belt. We travel around the entire equator. And the person on the North Pole, he is standing exactly at the pole. In an entire day, he'll be doing this, right? Right? But that's the fact. You won't notice it, but he is literally doing that in one day. If the Earth was spinning a lot faster, he would really feel himself rotating that way. But that's the fact that Earth rotates around its axis, and we all move in circular motion around the Earth. So going all the way down to the atomic level, this is one of the early models in chemistry. I'm sure you learned it in like maybe primary school that you have an electron and the electron moves around the nucleus. So if you model that as a very simple kind of orbital motion, we know it's not that case, right? We know the orbitals already, right? So we could say that, for the hydrogen atom, the radius is about half an angstrom. To be familiar with what that is, maybe. 10 to the power minus 10 meters, right? So 0.05 nanometers is half an thermodynamics. So hydrogen is one of the simplest atoms that we know. The period should be blazingly fast. This is about 0.1 femtosecond. So really fast orbit. So we can see a big variety of circular motions. Right? Even coming down to human scale, when you sit a car and it goes around a bend, actually that circular motion, even though you don't transcribe the entire circle, the part of the circle that you move around the arc of a circle is still considered circular motion. So when racing cars do that, well, they are traveling in circular motion. And of course, our very famous Battlestar Galactica, I believe this is the human part of the track. So if you take the human part of the track, oh wait, the blue is the Cylons, I think. Yeah, so the blue is the Cylons, then when you go around this part of the track, you only complete part of a circle. But it's still considered circular motion because you are moving part of the arc of a circle. So you can describe the radius in which you are moving as well as your speed and so on and so forth. Lots of kinematic terms that we can use. Right? Oh yeah, blue is Cylon. These are guys are hanging upside down. So many examples of circular motion. It seems like in the bigger scales in the universe there are, and in the smaller scales in the universe there are as well. Before we get started on talking about the kinematics of circular motion, we need to cover some of the skills, right? And I like to do this with all my classes. For each topic, I will summarize with them what are some of the skills that they need to do well in this topic, right? And actually, you learned all of these before in the previous topics up to dynamics. The first is being able to resolve a vector, taking a vector and splitting it up into two perpendicular components. Familiar with that? Okay, if you're not, it's time to get lots of practice to be good at this. Alright, drawing free body diagrams, isolate an object, sketch all the forces acting on it, and apply dynamics rules to it. And of course, by applying dynamics rules, I mean find the net force on it, right? And hence its acceleration. So these are the skills we'll need for an object moving in circular motion. Okay, we need to learn a lot of new terms today, but don't be too difficult. Don't be too worried. They're not very difficult. They are somehow related to the terms you already know. Starting which is displacement. So consider an object moving from this point A to this point B. It transcribes an arc of a circle S, right? That's the distance the object travels as it moves in a circle. Right? So in moving this arc of a circle, right, it also actually travels a certain angle. And we can label this angle theta. And of course, depending on how large the radius is, the length of an arc must be larger, right? You have learned a relationship in secondary school that relates the length of an arc to the radius of an arc. So we know displacement from kinematics. The new term we're going to learn today is simply angular displacement. It's the displacement in terms of radian or degrees or revolutions. So we use this equation S equals to R theta to calculate theta or delta theta, which is simply what we call angular displacement. You know what the unit of theta is? Is it degrees? It's radian. So when we use S equal to R theta, must recall that theta is actually in radian. But most of the time questions don't give us a measurement of theta in radian. It can give it to us in degrees. Or it could say that a car travels around the track twice every 10 seconds. And then that's in revolutions. So we're going to need to be able to master transmitting our measurements of degrees in angles to radians, to revolutions, at will. So we're going to go and take a look at this right now. So by defining revolution, one revolution is one complete rotation. We can even define revolutions for objects that don't finish a circle if we hypothesize the circle that they move in. That means just see the length of an arc that they move and take it as a ratio. Of course, the other two you should be familiar. 360 degrees for one revolution and 2 pi for another revolution in radians. Alright, so I've printed for you some examples to try. We'll go through this one. It's quite simple, so you just need to copy it down. I printed it for you, so no need to copy it. So, first one, express 0.75 revolutions in degrees and radians. So this is quite easy, intuitive. 0.75 revolutions is nothing but 3/4 of a round, which should be 270 degrees or 1.5 pi. So let's work it out. So we'll take it as a ratio of one revolution then multiply by the degrees of one revolution to get 270 degrees. You can do that the same for radians, but don't forget to leave your answer in radians, 4.7 radians. Okay, which is exactly 1.5 pi. Okay, easy. Is it too fast? You got behind? Alright, next, 20 degrees in revolutions and radians. So 20 degrees, take it as a ratio of 360 degrees to get the ratio of the number of revolutions, multiply by 1 revolution. So we get 5.6 times 10 to the power minus 2 revolutions. Okay, to get radians, we take it as a fraction of 360 degrees again, but this time we multiply by 2 pi. So 0.35 radian. So we need to be able to convert revolutions to radians to degree at will. Alright, last example, 5 radians to revolutions and degrees. 5 radians, take 5 divided by 2 pi. That's a fraction of a cycle. Times 1 revolution, we get 0.8 revs. Or 290 degrees. So the idea is very simple. Always take a fraction of the whole and multiply by the whole. Okay? Anyone confused right now? Alright, if not, I'm going to go on. Now let's take a look at a real example. I don't know how many of you still use analog watches right now. I'm wearing one, but normally wear a digital one. Just click on extra so much. Look a bit more dignified. So if you have an analog watch, you'll notice that it has a number of hands, right? And they are actually all executing circular motion because, they're moving in circles. So we can describe them with the terms that we have just learned. So let's consider this clock with an arm of 10 cm. That's roughly the size of your classroom clock. If the arm is 10 cm and the arc that the arm translates for this particular change in time looks like 820 something to 830 something, 15 cm arc. Can we calculate the angular displacement of this movement in revolutions, in degrees, and in radians? I believe I didn't paint this one for you, so I can give it a quick shot. Alright, so if I painted for you, we just go through it quickly. S, let S be the distance traveled by the tip of the minute hand. So if I want to find the amount of angular displacement traveled by the minute hand, all I need to do is find the amount of distance it actually traveled as a fraction of its circumference. So S over 2 pi r will give me 0.24 revolutions. So if I want to find the same answer in degrees, instead of taking the fraction of the distance over the circumference times 1 revolution, I'll multiply by 360 degrees, so it's 86 degrees. And 1.5 radians. So these are all equivalent. Right? So angular displacement can measure any angle translated. Now, just a fun tidbit of a fact. When we say objects in the sky move across the sky, right? They move a certain distance, right? It's very hard to say exactly what the distance are. But if you're going to tell someone, half a day has passed. So how far has the sun moved across the sky? We can use angular displacement to represent that. So actually, when the sun moves across the sky, how much angular displacement does it have? Under 80 degrees, 90. Sun moves across the sky, from one side of the sky to the other. It's 180 degrees, right? Or pi radian, or a half a revolution. Yeah? So in fact, right, for astronomy, right, when we describe how far objects are in the sky, we actually use a measurement of angle. Like you can stretch out your arm and it's supposed to be a certain measurement. I can't remember. If my researcher remember. Okay, never mind. It's supposed to be a particular number of angles, so we split the angle up into arc seconds and arc minutes to represent 180 degrees. So you get the idea that we can use angles to now measure distances, so to speak, because we have this idea called angular displacement. Right, if we have angular displacement, just like in kinematics, you have displacement, we must have this thing called velocity, which is the rate of change of displacement. So we consider the same motion, an object moves from A to B, describing an arc. Alright? Now, this object would move with a particular velocity along the arc. Right? So if it moves with a particular velocity along the arc, it must be covering the same angle displacement theta in a certain amount of time. Which means to say we can define angular velocity. The same way we define velocity is the rate of change of displacement. But in this case, it's angular displacement, that's all. So omega, this W-shaped thing here is pronounced omega, is the symbol for angular velocity. Alright, now first, its unit should be radians per second, just like velocity. Right, so what can we do with it? Well, we could define some useful quantity for it. Like, since we know that we complete one revolution in a certain amount of time, which we call the period, but we can say omega is 2 pi over t, where 2 pi is the radians for one revolution, right? And we also know this relationship that the frequency is 1 over t, so omega is 2 pi f. So frequency is like how many cycles I can complete in a second. If t is the amount of time it takes for one cycle, frequency is the amount of cycles per second. So it is just the inverse. So you should be familiar with frequency in secondary school. What is units? Hertz. That's right. Hertz actually means per revolution. Well, per second, which is actually revolutions per second. That's what we mean by hertz. Or cycles per second. So in secondary school, you learn hertz means second to the power of -1, right? But actually, it depends on what kind of things you're talking about. So in this case, it's actually number of revolutions per second. So omega, our angular velocity, is 2 pi f. Now, there's this idea called speed, and there's this idea called velocity. What's the difference between velocity and speed? Speed is the magnitude of velocity. So speed has no direction, but velocity has. So object moving in circular motion, of course, if you look at the blue arrow at any one time, it's actually changing its velocity because it's not traveling in the same direction anymore. So we can say that the velocity of the object is constantly changing. But what if I want to refer to the velocity of object at one particular time? Well, the name for that particular velocity is called tangential velocity. Tangential velocity because I'm taking the tangent to the circle. And the tangent to the circle should be the instant in which it's going to move towards the next part of the circle. So the tangent to the circle at any one time should give you the vectorial direction of the speed. So if you know the speed of the object, and we know the direction of the tangent of the circle, we can tell the velocity at that time. So we're going to call this a tangential velocity. Okay, the reason why we need this is because the object is not moving in a straight line. We need to keep track of its velocity. So we can call this the tangential velocity. I'm going to be using tangential velocity and speed quite interchangeably during this lecture. So if you're confused, raise your hand and ask me what I mean by that term. Alright? So I'm not going to keep track of its direction simply because it's going to keep changing its direction. So I'm going to use the word speed. So there must be a relationship between the speed of this object, or what we call the tangential velocity, how fast it's covering the angle, and the radius. Because you imagine if the circle is much bigger, of course it must travel a faster speed in order to cover the same arc in the same amount of time. Right? So we can start with our definition of displacement, S equals to r theta. Divide both sides by t, and we get this new relationship, V equals to r omega. Okay, it's not strictly correct. We should be actually differentiating both sides with respect to time. And of course, since radius doesn't change with respect to time, using product rule, we will get d theta dt, which is nothing but our definition of angular velocity, the rate of change of angular displacement. So this is the second relationship we need. The first is S equals to r theta. The second is V equals to r omega. So this is very similar to the way we define velocity, right? It's the rate of change of displacement. But now we can relate it to the radius, and we can relate it to the tangential velocity as well. So let's make sense of this. If I'm covering the same amount of angle per unit time, if the radius in which I'm traveling is larger, my speed must somehow be faster. Correct, right? It totally makes sense, right? Okay, logical. So let's summarize the equations we have learned. Angular displacement, angular velocity, relationship between angular velocity and period, as well as relationship between angular velocity and speed. So these are some of the basic equations. We need this, mainly, throughout most of our circular motion questions. Okay, they're new to you. But not that difficult, right? It's just like one step further from your regular kinematics. Alright, at this point in time, are there any questions? Okay, no, we're going to consider more examples after this. So, your sewing threads can be wound in reels, right? And those reels can be unwound. So, let's consider this case where I have a reel that is 1.2 cm in radius. Again, I'm unwinding it at 3 cm per second, which means I'm pulling along the string, and then the string from this reel is unwinding, right? And because the string and the thread actually has thickness, right? The reel gets thinner and thinner and thinner. I used to play my mother's stuff so when she was young and she did a bit of sewing. So actually I've seen this happen. It really, really happens. The thread is so thin, it really picks up some thickness after some time. So let's consider two cases. At first, the radius of this of the reel is 1.2 cm and later on is 0.4 cm. But I'm still going to pull at it with a constant velocity. Are you able to quickly calculate its initial and final angular velocity then? Will it be the same? If it's not the same, what is it? Take a couple of minutes to try it. Alright, easy peasy. So let's calculate omega initial. Omega initial is nothing but the velocity divided by the initial radius. So the initial radius is actually 1.2 cm at the start. So we should get an initial angular velocity of 2.5 radians per second. Okay, and we repeat this calculation for the final radius, but with the same speed. So you should get that as 7.5 radians per second. Too fast? Okay, right? Okay. So initially, right, paper and try. Alright, so that's example 3. Most of you got it. Some of you who are a bit more slow, don't worry. I know there are quite a number of equations you just learned. Of course, you choose the one that has the unknown that you want to plug into. So in our list, we have V equals to R omega. Because I've given you the speed at which I'm unwinding the thread, of course that must be the same speed at which the edge of the reel rotates. Right? And I've given you the radius of the reel itself. So as the reel rotates, it of course spins. And how fast it spins depends on the radius it currently is at. Of course it gets thinner and thinner and thinner. This question tells you that it rotates faster and faster and faster. So from 2.5 radians per second to 7.5 radians per second. It must spin faster. That's assuming I'm pulling the string out at a constant speed. Yeah? So that's what this example was about. Anyone still unclear? Alright, then let's take a look at the next example. Sorry, it's a bit unrealistic. We have a model car moving around a circular track of 30 cm. Okay, but it's moving at 2 revolutions per second, so it's a really fast model car. Right, so 2 revolutions per second. So we want to calculate the angular velocity omega given these two pieces of information, the period and the speed of the car. Alright? So after that, you can try this part yourself. What's the angular velocity if it moves with a uniform speed in a circle of radius 0.4 meters? They're not giving you that one answer. You can try it for yourself. So we just calculate A, B, and C and for now. Okay, give you a couple of minutes to try this. Alright, some of you have a bit of trouble making sense of the quantities. So don't be confused. Tangential velocity is normal velocity. It's just that because they're moving in a circle, we must give it a special name. Right? It's like speed. However, with an angular something, like angular velocity, of course I'm not talking about regular velocity anymore. I'm talking about angles. So it's angle per second. Right? So there are two different things we're talking about now. Angular velocity as well as normal velocity. Normal velocity unit is meters per second. Angular velocity unit is radians per second. So for this question, they asked us to find the angular velocity omega. So we already know the frequency. It's 2 revolutions per second, which means to say 2 hertz. So angular velocity is nothing but 2 pi f. So you can get it to be 12.6 radians per second. Okay, that's a good question. Typically in physics, when we say ratio or fraction, we actually leave it in decimals. But if it's not a final answer, you can leave the answer in pi. But unfortunately, this was part A, which means if you represent it as a final answer, just multiply it out. Of course, in your calculation, you can just leave it as pi until the end of the last step. Alright, if the teachers haven't told you, it's good to not substitute values in until the last step. Alright, so this is easy, right? You're using omega is 2 pi f, one of the relationships that you have learned already. Next, period. How is frequency related to period? They're inversely related. So it's half a second for 1 revolution. That's what period means. Okay, most of you have gotten this far. Okay, part C, speed. So speed, we'll use v equals to the amount of distance you travel over the time taken. But the amount of distance you travel in 1 revolution is nothing but the circumference. So the amount of revolutions you have traveled in 2 revolutions is 2 circumferences. So 2 times 2 pi r. Okay, that's how many revolutions the object did in 1 second. Because the information given was, it did 2 revolutions in 1 second. So if I want the time to be 1 second, the distance will have to be 2 circumferences. Right? So 2 times 2 pi r gives me 3.8 meters per second. So that's the speed of the object, or the tangential velocity of the object, if you will. Alright, pretty cool. You could also use v equals to r omega. Those of you who were a bit more sharp, you noticed that you calculated omega earlier. So you can just take it, multiply by the radius to get the same answer. Okay, of course you must get the same answer because they're the same physics. Okay, good job. Okay, lastly, I'll give you the answer to B, although I said I wouldn't. Alright? Now, the question says, what would be the angular velocity if it now moves with a uniform speed of 2 meters per second, basically now at a slower speed, and in a larger circle. So because speed and radius are related together, we can get the omega, the angular velocity, to be 5 radians per second. So use v equals to r omega to get it again. So we're just formulating the use of the 4 new equations that we have learned, that's all. Alright, but we haven't really learned anything new because we're just definitions from something we already knew, right? Which is normal displacement and normal velocity. So what I'm trying to say here is that in physics, our equations don't come from thin air. Usually it came from something we already know before. So if you're very, very smart, right, technically I haven't taught you anything yet today, right? Because all it came from the definitions of kinematics. So if you study kinematics, you should know this as well. This is just a very special case of kinematics. Right? So if you think you're good, you can check your answer with your friends to these very simple questions. I got 3 objects. They are on a turntable or a CD. Do you all know what CD is? Yes. So a CD player, the CD rotates at a constant speed, angular velocity, sorry. And these 3 objects, A, B, C, are on it. And they're at varying distances from the center of the CD. So what's the relationship between the speeds of A, B, and C? Okay, which one's faster, which one's slower? You can check with your friends before I give you the answer. imagine it like a CD, you know? How to be the button? He has to be the button, right? That's pretty easy. So most of you have gotten this. Since they all share the same angular speed or angular velocity, omega, we can use V equals to R omega, V equals to R omega to solve. The larger your R, for all the same omega, the larger the R, the larger the V, right? So, safe to say, of course, if you're traveling the bigger arc, you need to travel faster. So, C is the fast, A is slower than B, B is slower than C. Since R of A is smaller than C. I think you would have guessed it correctly, most of you. Even by intuition, you would guess it correctly, right? Okay, next question, a little bit less intuitive, but not difficult nonetheless. The minute hand, you know what minute hand is, right? Of a clock is 3 meters long. So this is one of those gigantic clocks. Okay? What is the angular speed of the clock? To know that, you need to know how long the minute hand takes to go around the clock. Is it 1 minute? It's not 1 minute, right? How long does the minute hand take to go around the clock? 1 hour. So it's 60 times 60 seconds. So you want to get the angular speed, you take 2 pi divided by the period, the time it takes to go around, is 3600. So you get 1.7 times 10 to the power minus 3 radians per second. That's for a 3 meter long clock hand. What if it was a 3 cm long clock hand? What would the angular velocity be? Yeah, it will be the same, right? Because look at our calculation here, we didn't use the 3 meters at all. The angular velocity simply wants to care about how much angle you cover per unit time. Of course, from the earlier checkpoint question, you will know that the longer you are, the faster you have to be. So if you are to consider the tip of the hand meter has a faster speed, of course the 3 meter long one will be much faster than the 3 cm long one. But they have the same angular velocity or angular speed. Alright, you can't find this in your lecture notes, this is just a recap question, right? So what have we learned so far? We are on the topic of circular motion. We are considering the kinematics of the motion, which means talk about displacement, velocity, and acceleration. Oh wait, we haven't talked about acceleration yet. Right? So it turns out that acceleration is the most difficult aspect of circular motion to understand. But I'll present you a series of arguments, and then you tell me whether you think it makes sense or not, alright? So the next part we're going to learn about acceleration. There's about 10 minutes left, so I'll go through with you the derivation of the acceleration first. Alright? But before we get started on this, all the examples that I showed you earlier, the sun going around the Milky Way galaxy, the International Space Station going around the Earth, and even the Battlestar Galactica going around its own loops, right? Are all these objects in their natural state? By their natural state, right? I mean, do they obey Newton's first law? Or are they compelled to move in a circle? Yeah, that's the question. Are these objects in equilibrium? Now going back to our past topic, right? Are these objects in equilibrium? Are they? What's Newton's first law? An object persists in its state of constant velocity in a straight line. Some of those objects, like the moon, it may be moving at a constant speed, but its velocity is not constant because it's not moving in a straight line. Right? This means it's actually not in equilibrium. It's not in its natural state. It's natural in the sense that it forms naturally, but not natural in the sense that it obeys Newton's first law. It is not moving in a straight line. It is not uniform. It is, however, moving at uniform speed, but not velocity. So we still call it uniform circular motion, but they're all in a state of disturbance. They're all in in a state of non-translational equilibrium. They're all having acceleration, right? If you're not having uniform motion, you must be having acceleration. So we can conclude before we go into this that all circular motion examples, they are accelerating simply because they're not moving in straight line. So if you're not moving in straight line, you must be accelerating. So we start first with one-dimensional kinematics. Throw an apple up, it has an upward velocity, but it has a downward acceleration g, right? So it's possible for these two to be opposite in direction. What happens? The apple slows down until it stops, and then it starts to fall down. Let's reverse the scenario. I drop an apple, its acceleration causes it to speed up before it hits the ground. So that's one dimension. How about two dimensions? A little bit more complicated, but basically I can say, at first I may have a velocity given by the blue factor, but because there is acceleration, the acceleration causes my velocity to shorten in magnitude. Until I'm at the top there, you can see the velocity is a minimum. And not only has the velocity changed in magnitude, it's also changed in direction. At first it was pointing upwards at an angle, then it was pointing horizontally, and finally the magnitude increased a lot and it's pointing downwards. So acceleration in two dimensions, right, can increase and decrease the magnitude of the velocity, as well as change the direction of the velocity. So that's what acceleration does. We've learned this in kinematics, in projectile motion. So far so good. One dimension, two dimension. Now we're going to circular motion. So when I have an object moving in a circle, even if I consider the motion of an object uniform in the sense that its speed is constant, I'm going to call this type of motion uniform circular motion, it's still not in equilibrium, simply because it's changing direction. So we decided that it's definitely undergoing acceleration. We now need to decide what the acceleration is going to be like. So if the acceleration were in the same direction of motion as the same direction as the motion of the object, this object would speed up. But if it speeds up, it's not uniform circular motion. So it can't be in the direction of motion of the object. Like in my argument, it can't be the same direction because if it is, it will speed up. It can be opposite as well, because if it's opposite, it will slow down. But my object is not slowing down. So there's only two directions left. Which two directions? Right, inside and outside, right? Either it's pointing towards the center or it's pointing away from the center, perpendicular to the direction of motion. So, of course, there's only one that makes sense, which means it's pointing towards the center all the time. So now we can see the vectors very clearly. These two vectors are always perpendicular, the velocity vector and the acceleration vector for uniform circular motion. That's because the object neither speeds up nor slows down, but it's just changing velocity. So we got one-dimensional case where acceleration can only speed up or slow down. We got two-dimensional case where acceleration speeds up or slows down and change direction. In our circular motion case, it doesn't speed up or slow down, but only changes direction of the velocity. So this is a special case of centripetal acceleration for circular motion. You go behind all right this. Anyone has any questions about this idea of acceleration? Right, I think the argument is show that it's perpendicular simply by saying that it can't be in a direction. Right, now, big thinking question. Is the acceleration constant? Is the acceleration constant? Its magnitude appears to be, right? The arrowhead is about the same size throughout my animation. But what about the direction of the acceleration? Is it always the same? No. Even though it's always pointing towards the center, I will still consider this direction changing. So the centripetal acceleration has a changing direction as well. So we're not going to go into the acceleration of acceleration. We're just going to say that centripetal acceleration is not constant. It may be constant in magnitude, but not in direction. That's all. Alright. So this type of acceleration, right, we call it centripetal acceleration. Okay, it's an acceleration that must always point towards the center of the circle in motion. Right, we have 1 minute left, so I'm not going to go through the derivation mathematically of this. It's not in A-level syllabus. I will start our next lecture with the definition of, the derivation of acceleration mathematically. Alright, so enjoyment support. See you later then. The end already, right? If you have any